Hello friends, welcome to this video on direct displacement based design of dual system. This is part 4. The previous numerical continues. Today we wish to complete this numerical up to the Excel level. So we had the 4 tables we discussed earlier. Out of these first 2 tables we have already completed. Today we shall carry out the table for frame ductility computation, and we shall compute the base shear and distribute the base shear. Let us recapitulate the previous example that we had taken. It was a 10-story building and the data were given like this. The most important design data is the drift, which is 2.5%. So this 2.5%, then Fy also will be requiring today 500 megapascal. We will require rebar diameter which is 20 millimeter. And height of story etc. already there, masses are there. We shall need the length of wall today 5 meter, and the depth of beam will be required. Length of beam 5 meter, depth of beam is 0.6 meter. The post yield stiffness ratio 0.1 also we shall be utilizing, and we shall be utilizing the spectrum of Eurocode 8 for soil type B at 0.4 G level of seismicity. So this data we shall use, that's why I am again reminding you. Now from the previous 3 videos, we have the information of the different parameters like the inflection height 21.6 meter. Effective height we shall not be requiring today. This design displacement delta D 0.532 meter. Equivalent mass 7302 kg. Overturning moment on the frame as tabulated in the previous videos 23.741 kilonewton meter. MW, the moment at the base of the wall 11.491 kilonewton meter. These values of moment frame and the wall frame are based on unit loads applied, and these are not the real moments but relative moments. The yield curvature of the wall 5YW is 0.001 per meter. Epsilon y equal to the Fy divided by Es, the yield strength of the steel divided by the modulus of elasticity of steel, which comes out as 0.0025. So now we will calculate the frame ductility given by this formula, mu Fi equal to delta I minus delta I minus 1 divided by Hi minus Hi minus 1. So this is nothing but interstory drift divided by the yield rotation of the frame, which is given by this expression 0.5 epsilon y. LB is the length of beam, HB is the depth of beam. So for every floor, ith floor, this formula will be applied and it will be calculated, and then over the floors you can take the average, which will give you the frame ductility mu f. So let us calculate the theta yf as required here. 0.5 epsilon y, it comes out to be 0.0104 radian. So let us go to the tabulation. The tabulation is like this: the floors, then height of the floors, then delta I as we calculated in the previous videos, and finally the mu f tabulation. For this purpose we shall go to Excel sheet. Yes, this is the Excel sheet for computation of frame ductility. The floors, then height of floors, then delta I values from previous videos, and here we shall calculate the mu f I for each floor. The formula is this, so we will apply this formula here, equal to short parenthesis delta I minus delta I minus 1 divided by the height minus the bottom height, parenthesis to be given, whole thing divided by theta yf, which is here. So we'll drag this for the other cells and get the, what is the problem? You did not put, I think, the dollar sign, that's why the problem. Well, that remains constant. Yes, so now we make the sum of this equal to sum and the average of this we shall take equal to the sum divided by number of stories, which is 10. So 2.209. So let us remember this value 2.209 as the frame ductility value. Now we calculate the wall ductility. For wall ductility we have formula. So this is the formula, mu w equal to 1 plus 1 by LP phi y w multiplied by theta d minus phi y w height of inflection by 2. So here theta d is the design drift, LP is the length of the plastic hinge of the wall. It is a distributed plasticity considered, so there will be length. Phi y w is the yield curvature of the wall, which we have seen, it was I think 0.001 in the previous video. So LP have two expressions given by this. dB here is Fy is Fy of the steel, dB is the diameter bar and inflection height. LW is the length of the wall, horizontal length of the wall. So out of these two, whichever comes less is the value to be used. The yield curvature of the wall is given by 2 epsilon y by length of wall. So setting these expressions for LP, we get one value as 1.386 meter, and the second value comes out as 1.648 meters. So lower one is this, so this becomes the value of LP. So mu w by the formula we have just discussed comes out as 11.245. What is this? This is the ductility of the wall. And if you remember, ductility of the frame we had already derived through the tabulation in the Excel, 2.209. Now the ductility of the equivalent single degree of freedom system, you remember we had converted the multiple degree of freedom system to an equivalent single degree of freedom system, which has its own properties like effective mass, effective height, effective time period, effective stiffness, similarly effective ductility. So we are naming this as mu es dov, given by mu w into mw plus motf into mu f divided by mw plus motf. Just weighted average, and if you put all the known values that we have already calculated, mw motf from the previous videos and mu w mu f just we have calculated, so it comes out the equivalent es dov system mu comes out as 5.16. What do we do with this? We get the trial effective time period of the system at the design point, that is at displacement delta d. So there is one formula available in the literature, n by 6 mu es dov under root, n is the number of story in the building. So if you put all this mu es dov here and this, then you get the value as 3.79 second. So this is the trial effective time period of the system. Now we have to calculate the frame damping and wall damping. So this formula are available in the literature. Mu f we have already calculated, and R is the post-tilt stiffness ratio. We shall see this through a diagram here, and the trial effective time period just we have calculated is this. So this through this formula, and wall damping, this die is damping, frame damping and wall damping. So similar formula is available, only changes in the mu w in place of mu f, and it is instead of 120 it is 95 divided by 1.35. So this formula certainly we can calculate. Now the R that we discussed, the post-tilt stiffness ratio, suppose the yielding is here, after yielding stiffness is K2, original stiffness is K1, so if you take the ratio K2 by K1, this is your R. Generally it is 0.05 to about 0.1. So using this formula and the known values, we calculate the damping in the frame 8.97, it is in percentage. Damping in the wall 13.74 in percentage. Now the damping of the equivalent single degree of freedom system by the similar formula, weighted average formula, mw xi w plus motf xi f divided by mw plus motf. So put the values and you get damping of the equivalent single degree of freedom system as 10.53 percentage. So for this percentage and Euro code 8 for soil type B and seismicity level 0.4 G, you draw the displacement spectrum. This you can do. We have discussed earlier videos how to draw this displacement spectra. So we have drawn it for this equivalent single degree of freedom damping that we have calculated 10.53%. And you know your design displacement. So this is the displacement axis. Spectral displacement is the design displacement axis. Your displacement is 0.532 meter. So at this level you draw a line up to this displacement spectrum and then go downward and come up to the time axis. So this time here is your effective time, t equal to 4.44 second. So your t is 4.44 second. They have calculated through this spectrum analysis. Now let us revisit the things. You had your effective time period trial, that was 3.786 second, and the t you calculated through the spectrum use is 4.44 seconds. They are not matching. So trial was having a little error. Let us compensate these errors by applying this in the formula. So in the equivalent, in the damping formula for frame, we use, instead of t trial, we use t, this 4.44 second. Similarly here, it will be 4.44 second, and you can calculate. Now it comes out as damping in the frame 7.11% and damping in the wall 13.73%. Now by the same formula we have discussed, weighted average, the damping in the equivalent single degree of freedom system is 9.26. So it is now lower. Let us see, again taking the displacement spectrum and see what is the effective time period. So we draw the displacement spectrum at the newly obtained equivalent single degree of freedom system values 9.26%. This is the curve, and you have your design displacement 0.532 meter. Draw a line from here to touch the design displacement spectrum, go downward, and this becomes your newly calculated time period. So this comes out to be 4.25 second. So if you compare, the old one was 4.44 second and new one is 4.25 second. These are almost close. We can stop here, or if you want, you can make one more iteration to make it still closer. So our final effective time period is 4.25 seconds. Now, if there is a term, the effective stiffness of the equivalent single degree of freedom system, it is given by this simple formula. Any k is given by 4 pi square m by t e square, m by t square. So here it is t and mass is me. So put these values as we have obtained already. T is just we have got 4.25, so it becomes this mass kilonewton per meter as the effective stiffness. And BB equal force equal to stiffness into displacement. So our stiffness is Ke and displacement is delta D, design displacement. So it comes as 85,233 kilonewton. This is your design base shear. Now you see in force based design also you get a base shear through the code, and the displacement based design also you are getting a base shear here. What is the difference then? Both are forces. This is a force. In the code based design you get that force through only consideration of forces, acceleration, etc. Here you are getting this base shear by considering a displacement, and this displacement corresponds to the design point where the stiffness also corresponds to Ke. So you are now getting a base shear which is compatible to your desired displacement parameters. So this base shear is to be distributed over the floors through this formula, where the number of stories is less than or equal to 10. This is the formula. So BB is distributed through a weighted parameter Mi delta I divided by summation Mi delta I. So you can make a table simply. These are Mi, then Hi, then Mi Hi values I have already calculated, and this is summation. So BB is this, then you can just get the formula, that formula just we have seen, and get the values of Fi. So all the columns are calculated, and finally you can make a summation here to check. I see that it is 85,233, which was our base shear, 85,233. So this calculation is all right. So these are the forces which are your design forces at the floor levels. You can put these forces at the center of the slab in some node, in some established node at the center of the slab. At each slab level, each floor level, these forces are to be put. Then you carry out the analysis and carry out the design. So this is what is the background before design going to the software. You cannot do without a software like SAP 2000 etc. actual design. So before design, the design forces are to be computed manually like this, maybe using Excel sheet, or you can make a C program or some program. Thank you very much for coming up to here with me. Displacement based design for a dual system, that is frame shear wall system. Please subscribe the channel, like and share the videos. You can put your comments and queries. I shall be glad to answer those. Thank you.